So can you guys see my screen?
Yes, sir, we can see.
Okay, right. So you should write P in the chat window in the first 5 minutes, right? And then I'll ask you to write somewhere in the middle as well, right? Okay, so we started the Fourier transform last time, Fourier transform, inverse Fourier transform properties. So today we are going to study the properties, but just to recap, these conditions are more or less the same for convergence. So if a, wait, I think I forgot to connect. Um, yeah, if we want to see if Fourier transform converges, so there are those conditions for point-wise convergence. The function has to be smooth, but because most of the functions are not smooth, they are discontinuous, piecewise continuous. So for piecewise continuous functions, we need these Dirichlet conditions, and they are actually the same. The only difference is that in Fourier series, we required periodic function, and all these conditions applied only to one period. Um, and here in this language, you do not see that one period thing because we don't require periodic function here. So those same conditions are mentioned without requiring a single period. So absolutely integrable, yeah. On any finite interval, the number of maxima and minima must be finite, and the number of discontinuities must also be finite. With these three conditions, we can guarantee that the Fourier transform will converge um, at all points, um, and the reconstructed signal. So it's not just the when you say Fourier transform converges, it has two meanings. One is that when you compute this thing, so if you compute Fourier transform of a signal, this we know this will be an integral, so this will converge. That is one way of saying it. But another way is the inverse transform. Inverse transform. So if I want to construct at time t the signal from the Fourier transform, so 1 over 2 pi minus infinity to plus infinity, the Fourier transform, and this is actually my Fourier transform x. So if I want to construct it from the Fourier transform, the original signal, this original um, this signal, because I'm constructing it, so let's put a tilde here to just to represent that this is the reconstruction. Now we are checking whether this matches the original signal or not. So if the signal satisfies these Dirichlet conditions, this equality will be point by point at all the points except for the discontinuities. Yeah. So for the discontinuities, you again will have to remember this thing. You cannot expect this inverse transform to give you the values, but at the discontinuities, you have to pick this equation, right? That is what you need to remember. So just to illustrate this, let's say I have a um, square function, right? And let me now change the color. And let's say this is the reconstruction. Yeah, so the reconstruction is x tilde and the original is x. These two match in the limit everywhere except at these jumps. And at the jumps, I'm not going to use inverse transform. I'll simply say x of, let's say this is the jump. Yeah, so this is minus half and this is plus half. So let's say I'm doing it here. So it will be minus half plus plus minus half minus divided by 2, and this will give me the reconstruction at minus half. This is how you need to make up. So now we finally move on to the properties of transform. And instead of deriving these properties, because the derivation is very simple, it will either use simple calculus. Some of the derivations might require complex integration, but you are equipped with both of those. You have studied calculus and you have studied CVT. So there is no point in actually deriving all these properties. Our purpose will be to study these properties, understand what each property says, and more importantly, how to use these properties. So the first one is very simple. It's linearity. So we had the same property in Fourier series as well. Um, so if you have two signals and if you happen to know their transforms, so a linear combination of the time domain signals will transform to the same linear combination. So it's very much standard. Time domain shifting. So if you shift a signal in time domain by an amount t naught, let's say forward. By forward, I mean to the right in the diagram. So the frequency domain will see a modulation, right? And you see this property is also very similar to what you saw in Fourier series. So you can see that the connection between Fourier series and Fourier transforms is important to understand these properties as well. So the same modulation, you can now easily say that shifting in time domain corresponds to modulation in frequency domain. And the signs must be kept in mind. This minus sign matches this minus sign. That's what you need to remember. And if you now apply the frequency shifting in time domain, which is, you can also call it modulation in time domain. So frequency shifting, no, the reason he's calling it frequency shifting is that the shifting is observed in the transform. In the time domain, it is actually modulation. So you can simply call this property the modulation property. So yeah, here the shifting is now in the frequency domain, and the signs are now different. Yeah, so if you have plus sign there, you have minus sign there. But this is something you saw in Fourier series as well. And you can even, you should be able to actually utilize this property conceptually. How should you think of it? So let's say I have a signal in time domain, and let's say this is a transform in frequency domain. So this is X and this is capital X. And now, and let's say this is centered and this is also centered. And now what I do, I I multiply this signal by some exponential j omega naught t. So of course it's a complex thing. So you will see actually two functions. Yeah, in one this will be multiplied with some cosine, and in the others, so one will be cosine and one will be sine. So let's say these two plots, yeah, together you have this complex signal, and in the frequency domain, what you see is that you will have this thing shifted. So instead of 0, it will now be at omega naught. Yeah, this is the frequency which was used to modulate. So this whole thing will simply shift to that. Yeah, the origin, instead of the origin, it will now be centered at omega naught. This is how you need to picture it. See, x of omega minus omega naught. So shifting in frequency domain. And the next is time scaling and frequency scaling. So if you scale a signal in time domain, you will see a scaling of the opposite nature in frequency domain. Yeah? And you will also see amplitude scaling. So here, if A is, let's say, greater than 1, so this will be compression, but there it will be stretching. And if it is stretching here, it will be compression there. And it makes sense, yeah. So compression here would mean that you have more frequencies, yeah. If a signal is compressed in time domain, maybe I can illustrate this here somehow. The plots will not be exact because I only want to convey an idea. So let's say this is some signal, and this is, let's say, the transform, and you compress this signal. So you compress it in time. Now the changes are faster. Compression means fast changes, and fast changes means higher frequencies, because fast changes require higher frequencies. So because this is frequency domain on the y-axis, frequency domain, so this signal has to actually stretch in the frequency domain. So compression in time domain will always correspond to stretching in frequency domain, and vice versa. Stretching in time domain will correspond to. So stretching would mean if I stretch this signal, I'm making it slower. The changes are now slower, so now it has to shrink in frequency domain because the changes are slower. So that's one thing which you observe, that scaling is of a different type. But this is also important. It's not just scaling, the amplitude also changes, and the amplitude follows a inverse. Yeah. So if it is more compressed, the the amplitude has to drop, and if it is stretched, the amplitude has to actually increase. So now why does this happen? Yeah. So the reason is that if you are stretching the signal in frequency domain, you are changing the area. And the area, if you actually, if it was squared area, if you, for example, square the transform and then you integrate, this will correspond to energy. You will see it soon. It's something similar to Parseval's relation. Parseval's relation. So that energy has to be compensated. That's why you cannot change the total energy just by compression. So that is why uh, you see this factor, and you can prove this as well. So, so take note of both these changes. Scaling in time domain corresponds to two types of changes in the frequency domain. Scaling in frequency domain, but it's actually of a different type. So compression corresponds to stretching, and stretching corresponds to compression. And the amplitude scaling is also of that type. And this absolute value is important. So it's only stretching or scaling. There is no reversal on the y-axis. And if you can remember, this property was only available in Fourier series. It was only available for a is equal to -1, right? Here in Fourier transform, it is available for a is equal to -1, for a is equal to +1, a is equal to 2, -2, 0.5. So the reason it's available is that both the time domain and frequency domain functions are continuous. So it's continuous time, continuous frequency, continuous time, continuous frequency. That's why everything is possible. In Fourier series, because the frequency domain was discrete, so you could not see this property in full action. You only saw one type, which was the reversal. In conjugation, uh, conjugation corresponds to conjugation, but with frequency reversal. So you have frequency reversal as well. Now, duality is also an interesting property. So here you see that in the time domain, you we typically use small x for time domain and capital X for frequency domain. And here what we see is that the capital X is seen as a function of time. So it means that if you um, let me just illustrate this with an example. Let's say I have a kind of signal in time domain and I call it X. And let's say I have a kind of signal in a frequency domain, transform. Let's call it capital X. And now I take this shape. I take this same shape to the time domain. So instead of rectangular function, I use this sinc function. So I'm just following this shape, but this time in time domain. So it turns out that that same shape of time domain will now become the frequency domain shape. Yeah, it's the same shape. So small x, so capital X comes to the left side, small x come to the right side. The only thing you need to see is the reversal. So this has to be flipped. And 2 pi, yeah, 2 pi will be, we'll see a proof in a while. I mean, the reason you need this 2 pi is that we know in the inverse transform you need that 1 over 2 pi. So this 2 pi will cancel that. Other than that, it helps you predict pairs. So if you see a Fourier transform pair, you get another Fourier transform pair for free. You just switch the two sides and add a 2 pi to the amplitude and a reversal to the frequency. So this will be very important. It will be, I think it will help, it will save a lot of time, this property, duality. Again, this duality in this form was not available in Fourier transform, in Fourier series, again, for the reason that it was a discrete frequency. Okay, time domain convolution and multiplication, they follow similar trends. The convolution in time domain corresponds to multiplication in frequency domain. This is what we saw in Fourier series as well. And multiplication in time domain corresponds to convolution in frequency domain. Here we see actual convolution, and this 1 over 2 pi is a consequence of those two factors. If we compare it with Fourier series, I think this was not convolution, but this was periodic convolution, because this usual convolution is not converging for periodic signal. So that's the difference which you need to keep in mind. Similarly, differentiation and time domain um, corresponds to multiplication by j omega in frequency domain. And just remember one thing, I have been saying this again and again. Whenever you see these tables cannot make any sense unless you attach a particular meaning to t and to omega, right? So if you say that this t is a real number, right, and this omega is a real number, then this table cannot make sense. Can you guess? Can somebody tell why? I have to write this table in a different form if I insist on this, because would t being real number means that this is not a signal. This is not a signal, and then this is not a signal. So you lose everything. So then you have to bring in that notation every time. That is very boring, right? Omega, omega. We don't want to do that, right? So what is the easiest way to write this table? Is to stop interpreting t and omega as real numbers, but only interpret them as indeterminates. So t is a real indeterminate and omega is also a real indeterminate. We're not supposed to plug or substitute any values because indeterminates don't allow any substitution. And then you can, the advantage of that is that everything you see here is a function. Yeah, there is no number here. So frequency domain differentiation. So if you differentiate the frequency domain, you see multiplication in time domain. Do you, if I ask you to connect these two properties to this property, what will you say about this? It is very tempting to expect that these two properties are actually a consequence of that, or in similar way, in similar fashion, these two properties are consequence. That is a wrong way of thinking, because many people think that way, but that is wrong, because these duality is about the actual transform. These are not the actual transform, these are just properties. Yeah. So properties have to be derived separately. So if you want to derive this property, you have to start with Fourier transform and then differentiate it, and then you start apply the transformation, and this differentiation has to be somehow dealt with by the um, integration by parts. Yeah, you need integration by parts to actually deal with this thing. Now the most confusing part is this last pair, right? So I multiply, no, I differentiate, and if I differentiate in time domain, in frequency domain, I just see a multiplication of um, j omega. So if I now say, okay, if I multiply, if I differentiate twice in time domain, I should observe multiplication by j omega twice in frequency domain, right? And I can even move on to say that, okay, if this is, if I differentiate n times, I should observe multiplication in frequency domain by n. And now I can say, okay, what if I set n to n minus 1, right? If I set to n to minus 1, so what should I get? I should get integration in time domain, and I should simply see a division, because j omega to the negative is 1 over j omega. This is the only thing I should see. Why should I see this extra part? Yeah, that is the problem. Anyone who can guess this, the reason for this part? And I'm just wondering whether you have seen this part in CVT. In CVT, I'm sure you had this property, right? So was this property there, one of the properties? Hmm? Can anybody confirm that integration was time domain integration was a property there?
Sir, we didn't study any of them.
Huh? Sorry?
As much as I can recall, we didn't study any one of them. Baki students can confirm as well.
Yeah, but you're telling me that you studied transforms without properties?
Yes, yes, sort of. We just learned how to solve question, how to integrate, and how to actually compute stuff. And we didn't go like that deep into the properties.
Okay, and even in Laplace, but because I remember this convolution multiplication. This is, I think,
Sir,
everybody.
we only studied from notes in CVT,
Hmm?
and as far for Laplace, we did linear algebra and differential equations, both the same course, and we just actually
Also,
skimmed the Laplace transform. We didn't study it
for you,
deeply.
linear different algebra and differential equation was in the same course.
Yes, sir. So we didn't study Laplace transform that deep.
Yeah, but I can check the outlines. So you remember, whenever you study a course, you should remember this. You should know the outlines, and then you can ask the instructor for the outlines. Because
Sir,
as
when They were actually taught to us, but it was the last week right before the exam. So we just went like upper, so we just skimmed through stuff. And that's how we studied Laplace and these Fourier transform and their properties. We were just crammed the notes as Saad mentioned.
Okay. So you're telling me that all the course was based on notes, and so, but it was not based on the textbook, right?
Yes, sir. Sir, CVT course was only based on notes.
Yeah,
Sir
but
said that you should only review my
courses
notes.
are based on notes only in schools and colleges. This is university. This is not college.
Sir, that was the problem. I asked sir to give us a book, but he refused. And I also
So
told
did you
you,
go to your head of department for this?
yeah.
And what did he say? Did you
No,
go
we
to your
didn't.
salary?
We didn't tell the HOD.
Yeah, so I mean, you were supposed to go to the HOD, right?
So he actually did share a book when we asked him to, but then he was like, "You just focus on my notes. That would be more than enough. If you
Yeah,
want to refer to the book, that's your choice, but just refer to my notes."
yeah,
That's
but
what he
you
told
have to
us.
go to your head of department. If you go, you can go now. This is not acceptable. This approach, well, why are you sharing a book if you're not following it, right? And the whole idea of university education is to make students independent, and students cannot become independent if they have to follow notes. The reason I give you these two books, I
Yes.
want you to read the books. I want you to compare. I want you to spot mistakes in the books, my mistakes, author's mistakes, because books are written by humans, yeah, they're not written by God. So if you rely on notes, then it's a serious thing. You are actually mature, and I would say even if I do something like that, you should go to the HOD. Okay?
Sir, maybe the reason for another term is because we're dividing by omega and omega can be zero.
No, that's not the reason.
Can omega never be zero? J omega.
No, omega can be zero, but then if that is your argument, then we should not have this term in the first place. We should have those two cases, right? Just like we do that. By your argument, we should go like this, right? That if omega is non-zero, right? I should see x of omega divided by j omega, right? And if
Yes.
omega is zero, I should get another term, but that is not happening, right? You see both. So why do you have this term? I want you to think about it. This term has a special thing in it. That will explain everything. What is unusual in this term? Hmm? Can you tell me which part is unusual in that term?
Delta, direct delta.
Yeah, delta. So delta itself is unusual, right? Delta is zero everywhere except omega is equal to zero. So when omega is equal to zero, this delta will shoot to infinity, right? And when it shoots to infinity, then it doesn't matter whether you have this term or not, right? This whole thing becomes infinite anyway. So having this term divided by zero or not divided by zero doesn't make any difference, right? You get the point now?
Yes, sir.
And when omega is zero, then that thing is zero, and then you don't have division by zero. So that's why you don't see those two cases. But the question is, it is not just explaining what this term means. The question is, why does this term come out in the first place? So why should we see this term in integration? Yeah. Remember, the reason is this lower limit is minus infinity and the upper limit is t, but t, we want t to be running. We don't want t to stop. So t can be anywhere. So this integral will definitely have issues of convergence, right? Last time I did discuss the issue of convergence. You don't have an issue of convergence with differentiation. Why? because you just start with a function, you want to find the slope at every point. Yeah. So if you follow those Dirichlet conditions, then there is no area which is accumulated. The issues of convergence always appear in integration whenever you are integrating, because in integration you have these things get accumulated and they get out of bound. So because this is an integral, the integral, it is possible that things accumulate in such a way that the usual Fourier transform doesn't work. So you have to go for generalized transform. Remember, I last time used this term, generalized transform. And we even had a pair, if I now recall. Let me just remind you one thing. In the last lecture, we had this pair that if you start with the Dirac delta and you compute the Fourier transform, you will get basically 1, the constant function. And this was easily done. But when we started with 1 constant function, the Fourier transform was 2 pi times delta of omega. And this is the reason 1 is a signal which never dies down. So the transform will never convert. So you can never compute the transform of 1 in the usual sense. You can only do it in the generalized sense, generalized Fourier transform. And the generalized Fourier transform has to use some indirect tricks. And one indication of generalized that you have to see this delta in it. And that is the same delta we see here, right? Okay, so I'll get back to these properties. Let's see some. I think these properties are very much the same. Parseval relationships. Can you connect this with the relationship for Fourier series? Let me write this down there above, okay? So for the Fourier series, this integration was actually summation. No, it was not summation. It was summation on the right side, I think. On the right side, it was summation, and it was that ck squared, right? And all possible values of k. And here it was, if you remember, for Fourier series, it was this integral, and the integration was over one period because this thing is impossible for a periodic function, and then you had to divide by t. So this was actually the average power, right? The average power. Why can we have this integral in this case? Why don't we do something like that? Any idea? And if that is the average power, what is this quantity? Can you recall the name of this quantity for any signal?
Energy.
Energy. So this is the energy of x. We can compute the energy of x here. We could not compute the energy of x in Fourier series. Why? And that is the reason we had to compute the power. Because in Fourier series, the signal had to be periodic, and the energy of a periodic signal is, tell me.
Infinite.
Yeah, unbounded. So the only thing you can do in a Fourier series is power, right? So here it is energy, and the energy can also be computed in frequency domain. So now can you give meanings to this thing? What was the meaning of this ck squared in Fourier series, if you remember? Because this is power, right? And you are adding these terms, so each term must be power, right? But power of what? Power in that frequency. Power in that frequency k. So k पे जो frequency बनती है k ओमेगा नॉट, उस frequency की वजह से जो power आता है वो आप यहाँ पे ले आए और सब सारे powers को add करें. So here we are not adding, we are integrating. So can you now tell me what is the meaning of this thing? Can we call it, so if this is energy on the left side, can we say that this is the energy contributed by frequency omega? Can we do that? Hmm?
Yes, sir.
No, you can only call it energy if you are adding. There you are adding it. You're not adding it, you are integrating it. So you are multiplying this quantity by d omega, and then you are adding it. So with the d omega, you can call it the energy, right? I'm integrating not just x of omega magnitude squared. I'm integrating this whole thing. This you can say is the energy, right? Contributed by frequencies near omega, right? So if this is the energy, the tiny energy near omega, I mean, you should think of it in this way. Let's say this is the frequency axis, and this is omega. So you have to find a small, tiny interval, and in that interval, you get this energy. So if this is the energy, you have to divide by d omega if you want to give meaning to x squared. So dividing by omega means that you are actually looking at energy density. This is what I told you last time. Energy density, not energy. So that is the fundamental difference between Fourier series and Fourier transform. In Fourier series, the coefficients, when squared, when you take the square of the magnitude of a coefficient, you get the power of that frequency, of that harmonic. But in Fourier transform, if you take the Fourier transform at a frequency and then you take the magnitude and then square it, you don't get the power, you don't get the energy, you get the energy density. Energy density, right? So this relationship tells you that if you are reconstructing a signal from the Fourier transform, uh, the complete reconstruction has to follow this integral. And if you don't want complete, let's say you take this not from minus infinity to plus infinity, but to some finite range, let's say from omega 1 to omega 2, then this will not be the total energy, but it will be some energy. And that's what you got in the assignment. In the assignment, you were asked to find all the harmonics, yeah, which captures some 98% or 95%. You can have similar question in Fourier transform, right? So if I know the Fourier transform, if I know the Fourier transform, if I then take the square and if I integrate it over the full real line, I get all of the energy in the time domain signal. Of course, this 1 over 2 pi is also part of it. But if I integrate it over some finite interval, then I will get some significant part of the energy, but not all of the energy. Okay, I think and that is why understanding Fourier series and the properties are so important. Because without that understanding, you cannot link, you cannot make sense of these properties either. So even symmetry, this is very similar to Fourier series. If the time domain signal is even, the frequency of the Fourier transform is also even. If the time domain signal is odd, the Fourier transform is also odd. And if you can recall from Fourier series, this was only possible when x is real, right? If x is not real, then you cannot have an even or odd property. And the last property is also very similar. If x is real, the Fourier transform must be conjugate symmetric. And what does conjugate symmetric mean? Can anyone recall that? Hmm? What this means is that if you take the conjugate and then
Reversal.
and then you reverse it, then it should equal the original one. And this is a requirement if x is real. And the reason for that is that when x is real, the conjugate becomes equal to x. So that was actually the reason for this property. It's actually a consequence of this property. I'm now highlighting it. If you apply reality to this property, yeah, so reality would mean a signal is real when this signal is equal to x of t. So when this signal is equal to x of t, this has to equal x of omega. That's a consequence. Now we need to discuss certain pairs.
Sir,
Yes?
so अभी जो आप बात करते हैं Parseval की, so the total harmonic distortion you mentioned while talking about Fourier series. So the only difference here in Fourier transform is that since for series we had like a summation and here we have an integral because of the continuous nature. So can you like pinpoint the main difference again?
No, the reason you integrate here is that transform has a different meaning. You are summing it because each term in the Fourier series is directly a harmonic. Here, you see that x of omega is itself is the density. Yeah, ck was the spectral coefficient. If you remember the name, spectral coefficient. Ck tells you how much of a particular frequency is needed, but x of omega is not the coefficient; it is the density of the coefficient. That's why you need to integrate. That is one difference. This 1 over 2 pi is needed here. Again, the reason is this d omega. Actually, this d omega is angular, and you should actually need df. So that 2 pi is simply because we are using omega instead of f. So that is obvious. And the percentage rule is very similar. If you let's say are asked to tell me how many frequencies do I need to, let's say, capture 95% of the power. So I have to figure that out, and then it will not be from minus infinity. It will be from some, yeah, minus omega 1 to some plus omega 2. So that's all. I don't think there is any other difference. But the difference is a consequence of the fact that a Fourier transform is a density. That one line will help you everything, yeah? Fourier series are coefficients and Fourier transforms are densities. So if you remember this thing, everything falls in place.
Okay.
And now pay attention to this table, yeah, because we would like, actually, you will be expected to use this table of properties and this table of properties. So here, this is something which we derived last time. So there is no point in repeating this, right? I just started this a while ago. And instead of going to this next property, I'll just go to the third property because this is related, right? This is now the dual. I bring that one here, right? So you can now see the duality here. I bring that one here, this delta goes to the right side, and because delta is actually symmetrical, so even if you put this minus sign, remember in duality you need a minus sign, right? Do you see the minus sign? Reversal. So when you apply that to delta, it doesn't matter. That's why you see this without the minus sign. But 2 pi is there, right? Now, instead of coming to this point, let's come to this point. So let's start with the property 4. This property 4. You can derive this property very easily. This will turn out to be, if you think about signum, the signum function, I think it's 1 and minus 1, and it is 0 here. I think it is, you can easily see that this is a um, this is you can connect it with this with differentiation or integration with something. So I don't know if I can recall this, but can you think about as a function which when you differentiate you get this thing? What was what was the connection between u and delta? Remember that?
In derivative,
It was the
probably.
derivative, right? So this, if you think about this thing, this is actually u of t, right? This part only, and this is u of minus t with the minus sign, right? So I can easily say that, let me put it this way. I can easily say that signum of t is simply u of t minus u of minus t, something like that. And then I connect it, then I can connect it with the uh, differentiation. So if I differentiate this, I will get delta here. And what do I get here? Something like this. And then you apply that property of differentiation. Yeah. If this if the transform of signal is x, the transform of the derivative will be j omega x and something like that, and you get this thing. So I think this is there is this one sign missing here. You need this minus sign because you need to apply the chain rule, right? So delta of minus t is delta. So this actually turns out to be 2 delta t, 2 delta t. Because when you apply the chain rule, u of minus t is delta of minus t, but the chain rule requires another minus. This is plus, and delta of t is equal to delta of minus t. So it's actually 2 times delta t. So you see the Fourier transform of delta is 1, so it's 2. And this means that x of omega is 2 divided by j omega. And that's the property you have. This was very sketchy, so I would highly recommend you to read the full proof in the textbook. Yeah. So what I want you to think about now is that the reason this j omega is in the denominator is this differentiation property, right? This differentiation property. And the reason you have this 2 there is that when you look at signum, you actually have 2 step functions, right? So they're both added somehow after differentiation. Now look at the signum function again. Each one of them has a problem of convergence, right? U of t has a problem of convergence if we think about the Fourier transform. This will also have a problem of convergence if you think of the Fourier transform. But because they are in the opposite directions, they somehow have a zero average value, right? The average value is 0. That's why you don't see this term. This term is 0. But if you try the Fourier transform of the unit step function alone, there is no hope that it will converge because this is 0 and this is 1. So this 1 over j omega will only represent the fact that delta is the derivative. So ये जो चीज है ना, ये तो आपको यहाँ पे मिल रही है 1 over j omega के फॉर्म में, लेकिन that's not the only thing that is going on. Yeah, you need a term which represents the fact that the Fourier transform of unit step function will not converge. And that is why you see this delta. So I can also actually ask you to think about it in this way. Look at this function 0 and 1, and this is 0. So what you can do, you can express this as a sum of two functions. You can express this as a constant function and the signum function. So if this is minus half and this is plus half, and if this is plus half, so you start with half signum and then you add 1 to it. You get something like that. So you already know the transform of half signum, and for this you need the transform of the constant. So remember, for the constant it was 2 pi delta of omega. So for half it will be just half, it's just pi. And for signum we just saw 2 divided by j omega, but with half it will be half, so it cancels. So 1 over j omega plus pi of omega. Pi delta of omega, right? 1 over j omega, pi delta of j omega. So I think it will really help you if you derive these properties yourself by using that table. So if you can derive each one of these properties, then you are done. Then you can solve any question, right? And if there is anything which is, impossible for you to complete, or if you don't follow the steps in the textbook, you can always ask me either in the next lecture or drop me a message in GCR. I'll then upload my version of derivation. If you don't follow the derivation in the textbook, I think all these properties have been derived, but I want you to do yourself. Here, we only want to make sense of it in the language of signals and systems. So, can you suggest a quick way of justifying this property? And I want you to think about only. So let me remove everything. I want you to look at only the first one and see if you can justify property 5 from property 1. Which property do you need to go from pair 1 to pair 5? These are not properties, sorry, these are pairs. Which property do you need? No, not, sorry. It's a mistake. From property 3. So which property do you need to go from pair 3 to pair 5? Let me highlight that only. It was a mistake. Any idea?
Modulation.
Modulation. You multiply by exponential and the frequency domain must see a shifting, right? So that was very good. Okay, now combine, sorry. Which property do I need to go from 5 to 6? Can do that. Cosine can be expressed as, tell me, Euler formula, right? Divided by 2. Now tell me, which property do I need to go from 5 to 6? I need two properties. Linearity, right? Because I'm adding two functions and divide by 2. And what do I need to go from exponential to this function?
Reversal, time reversal.
Reversal. And time reversal is a special case of time scaling, right? This is a special case of time scaling. So I need linearity and time scaling, in other words, time reversal, to go from property 5 to property 6, right? Now to go from to get to 7, I can follow two paths. I can either go from 6 to 7 directly, right? Or I can go from 5 to 7. If I want to go from 5 to 7, I simply need linearity and time reversal. But if I want to go from 6 to 7, what do I need? Tell me. Hmm?
Negative derivative cos of sin.
Negative derivative. Negative derivative. And how will I explain this? Hmm? What do you see there when you apply derivative? You see this thing, yeah? J omega, right? J omega. So if I apply this, what should I do? Remember, this is simply negative derivative cosine omega naught t, right? So what should I see here? I should start with this and multiply by j omega and then multiply by negative, right? So I see this minus comes here, this minus. And now you need actually shifting property, right? So this omega, when it multiplies this, you will only need this omega will only survive at omega naught. So this will be omega naught when you multiply it by this. And when you multiply it by this, so maybe this root was not a very good root. The problem with these deltas is that when you have deltas involved, there are many equivalent functions which will algebraically look very different. If you plot them, only then you realize that they're actually the same. So I will actually discourage this second method, okay? Because then you have to follow this shifting property. This one I already discussed last time. So I would now ask you to write your presence in the chat window again, right? So let's get to the last two properties. Rectangle I already discussed many times I think in the first lecture. If you have a rectangular function and when you stretch it, yeah, so that the window the width is not 1 but t, and it will minus t by 2 plus t by 2. So this turns out to be the sinc function. And to go from 8 to 9, you need duality, right? You bring this here, you bring this here, and you make those adjustments. This is okay. What property do you need here? Can somebody quickly tell me what property do I need here to derive this?
Laplace.
Huh?
Laplace.
Laplace is not a property. You know this, yeah? You know this property. This pair. So how do I go from this to this? The only thing you can try is multiplication, right? Why can't we say modulation? Why is modulation is not an option here? This is a conceptual question.
Was its time domain?
Sorry, say it again.
Complex exponentially.
Yeah, this is not necessarily complex, right? So although he says real part must be positive, but I can use real A as well. So this is not a good idea. So you have to go with multiplication. You go with two functions multiplying. But the problem with that is that you need a pair for exponential minus at. So maybe that's uh, either we need a pair or we work this out directly. So this has to be derived without using any property. You have to derive this directly. And you will be surprised to know that deriving this is much easier than deriving that. Sorry, what is that? Although it is simply u and it is u times exponential minus e, but this is simpler. Why? Because that u alone is the transform will not converge because the signal does not converge. But here you multiply u with a decaying exponential, right? With a decaying exponential. So instead of u, you multiply it with a decaying exponential, and this exponential will now help this signal drop, and the Fourier transform will be just a traditional transform. It will not be a generalized transform. That's why you don't see the delta there, right? I think we are done with today's lecture, right? So in the next lecture, I'll decide whether I need to have some more examples, because maybe we need at least 2 or 3 examples to apply to particular questions, and then you will learn how to apply these pairs. You need 2 things. You need to start from the correct pair, because if you start from an inappropriate pair, then no property will help you. And then you need to learn how which properties are relevant to go from one signal to another. Okay. So see you next time.